Very good morning to all of you. So our next topic is fluid kinematics. So previously we talked about introduction parts. Introduction, there you have properties. There you have properties that how the what properties are there of the fluid. Properties mean density, viscosity, and some basic laws, just like Newton's law of the viscosity. You have saying then surface tension there, and then viscosity. And these are the two things you have: the density, viscosity, and the surface tension. These are the two things, and based on that, you will study something capillary rise, some flow due to this viscous fluid actually. So that is some basic. After that, you talked about that first you will hold the fluid in some container reservoir. So that's you have come there. The fluid statics actually. So what will happen when fluid is in the rest actually? So there you have pressure, mainly pressure actually. So if you have rest, so fluid will have its own weight, which will try to press the body downwards, and then you have insides. You will feel pressure also because the pressure acts in all sides. So you will have some sort of the support to those type of vessels actually. So statics is designing of your all storage vessels actually. All storage vessels means your dam is also one sort of the storage vessel that is in the open condition type of thing, right? So you are mainly designing all storage items in case of fluid in the statics by doing the force analysis. So we did for all type of the surfaces there, the plane surfaces, your the circular surfaces, with spherical case also, cylinders also, curved surfaces and plane surfaces. Practically you can classify into curve and plane. And their point of action, then how would you provide the support to sustain those particular actually bodies where you have to store your fluid actually. So once you store, so storage will not serve your the purpose actually, uh, because once it is stored or to get the things stored, you have to always do some motion, some transportation of the means fluid. So that comes in the category of your kinematics parts, mean how the things would move within the fluid is velocity, is acceleration, what direction the fluid will move, what do we need to focus actually. So that will be, we will try to cover in this particular chapter, that is fluid kinematics. So references are same as you have previous one. So one is by this Eunice Sengel actually. So this you have one book here. So that is Fluid Mechanics Fundamentals and Application. Next is McDonald Fox. Other one is Mulson and Young actually. Then McAbey Smith, and then Ron Darby and Niels D. Neighbor actually. So these are the references books. So you can have any one of them actually, which will serve your purpose. So objective of this particular uh, chapter is first to understand the material, the derivative, and transforming between Lagrangian and Eulerian difference. So material derivative means all your laws actually what are being framed, just like your first law of motion, second law, third law. All these laws are with basic fundamental laws, mass conservation and force conservation. This everything actually are framed for a substance actually. So you have always taken a system or substance whose mass remains constant. So that mass means, so that mass is coming from there, the material. You can see the substance also, that's in that case is called substantial the derivative. So if you are putting d upon means d upon dt or the something, so you are calculating derivative of the something. So in that case, you are calculating for the material, how the materials or substance velocity would change. So that's called in the material the derivative. Next is distinguish between various type of flow visualizations, and means once it is flowing. So we have to identify what type of flow. So there you have talked about two type of flow. There are three actually, if you want to classify the measure. So one is the laminar flow, other one is the transient flow, and next one is the turbulent flow. These are the basic classification three. In these three also, you want to know exact flow also, that how my flow is. So you want to know that much more correct. So you can have some cameras, you can put some tracer particles or colored elements. So you can say exact pattern in that way. Then once you have fluids, so you want to say the motion, that how would it move. So that could be maybe a linear motion, or maybe a transformational or the rotational. And then you can have rotational have means you can distort the fluid, you can moving in a circular path. Then you have transformational, you are just transferring from one place to the another place, just like a packet only. Other one is the deformational part, that you are changing the geometry of your figure, just like that. So primarily you have this type of the rectangle, you have moved it completely, but now you have changed, compressed kar diya or expand. So that could be possible that the fluid may get compressed, or let's say a fluid element may get compressed or expand. So that's called deformational part. So that also we will study. Then you have rotational. So that is again the flow patterns, because that these two can also happen, because once you are doing the fluid flow, so either would be a rotational just like that, or a rotational, because these are the two possible type of flow could happen only, or a mixture of two also sometimes could be possible. Okay. Then we have Reynolds transport theorem. Then it would be used to just to first to understand what is it actually, and then we will apply it to do the various calculations of forces actually, forces or velocity. So these are primary means objective of this particular topic. So first we were talking about Lagrangian and Eulerian means. So Lagrangian means just like that. In this particular system here, you have these particles. One is this particle, then you have black, then you white one, then you again gray one. So you have marked some particles which are of different type of, either you can give the numbering actually, or you can give different colors. So these are your total particles of the fluid. Fine. Let's say here, so you are focusing, let's say you have particle A, particle B, particle C. You have three particles you have highlighted. Now, let's say these three particles, now you want to focus that where, how this particle A would move, where will it go, so its motion, your trajectory, everything. Now, same thing you want for B also, what is happening with B. Same thing for C, what is happening with C. So means you are focusing on individual particles, that what is happening to each my individual particles, and I want to have a track on them. So this approach is called Lagrangian approach actually. So here you are focusing on individual particles, and this approach need a lot of the equations. Means by chance you have three particles. So each particle, what can you write? You can write one force balance. Yes or no?
Yes, sir.
Newton's law of the mean the motion, you have three, right? That V equal to U plus AT,
Yes, sir.
then what is that? V square plus U square plus 2A something. Then you have one from S, distance traveled in Tth second something, so, right? S equal to UT plus 1 minus, I think, 1 by 2. Okay, I also forgot that thing actually. So you have that also. You have three. That is the law of the motions. You can also do the force balance also, that your the momentum change and everything. So for each, then you can write the one for energy balance. Energy also need to be calculated. So each particle you can write your mass balance, your force balance, and your means the energy balance. These are three main balances actually. So each particle you can write three, and now you have three, so you have nine equations. then based on that you can keep on increasing and increasing because fluid have enormous number of particles. So in that case, your handling of these equations and solving them is becoming tedious and a lot of computational time. So this need to be done only when you really need it actually. So this most of the time is needed in case of pollutants actually. So some pollutants are harmful, they are coming from a particular furnace or let's say coal-fired plants. So there you have a lot of burning of fuel. So you have a lot of pollutants are coming, just like your NOx, SOx, carbon dioxide, and nitrous oxide. Those are harmful. So in a particular concentration there, then you also dust particle also because the 100% is not burned. Some fine particle also goes. So many pollutants, and you are focusing them. Let's say they should get dispersed in entire area so that their concentration at a particular place should not go beyond a acceptable the limit, right? So in that way, you are focusing on Lagrangian approach actually. Or sometimes you want to trace the movement of a particular particle, how these flow patterns are moving. So in that case, also you want the Lagrangian part. Uh, So that is the Lagrangian. Then you have another one is Eulerian part here. So I can explain with that figure only. So now you have these particles here, all these particles in this particular system there. Now you are just focusing only at this boundary. Let's say you have this boundary and their boundary here. So you are just focusing, let's say, what is coming in, what is going out. Okay, so you can focus here at this cross section that how much mass is coming, what is the velocity at that particular point, what is the pressure at that particular point. Now you are entrance, you are and focus on exit point. What are these parameters at this? So you are just focusing only at boundaries. So if you are not interested in between here, which particle is moving slow, fast, and no, you are not interested in that. You want the total parameter at this cross section and entry and exit. So that approach is called actually Eulerian approach, and that's just like your the semester system or a degree system. Semester means once you've been study throughout the semester, and at the end of the day, your parents and everybody want what is your marks. So if your marks is good, everybody is happy. Good or bad, you can leave for time being. They are focusing on marks. Okay, you got admission this time. Now you give an exam. Tell me your output. That's all. So this is called Eulerian approach. Lagrangian means now you will say, okay, how much were there in your mid semester, how much were there in your test one, how much were there test two, day-to-day performance and all this. That too for individual students of the class. So that's called Lagrangian actually. Okay. So that's the difference. Now each fluid particle would have these actually fluid property. There could be many more, but we are interested more only in flow. We need a pressure because pressure is the driving force for us. Then once you have a driving force, obviously you will have a velocity there. And velocity, now if velocity is with respect to time and all this, so obviously you will get the acceleration part, right? So these are the three things you have in case of flow of fluid. You have the point, without pressure, the thing will not flow. Velocity and acceleration. So in case of the fluid, actually you have these three main things. One is your pressure, that is your driving force, and then velocity, then acceleration part here. Now all of these actually, that pressure, your velocity, and acceleration are the function of three things mainly. There are one more parameter. So one is three coordinate x, y, z. So and that is the time. So if your behavior or fluid is time dependent or not. So let's say you have unsteady state operations. So that you will have a time function also. So in your whenever your plant is working and all this, Most of the time it goes through the unsteady state. You are continuously providing energy to the fluid actually to make it flow. So then each component, let's say you have velocity vector, have three components. One is the x direction, one is for y direction, is j cap, and k direction, k cap. And all of these could be the function of x, y, z, and t. Okay. So your u component of velocity would have all four factors in that. Same thing v component, the same thing for w. So all of them can have all these four variables at max. These are the maximum actually mean the dependency. So let's say for this one. So what you have here, let's say this is your fluid element, and let's say at this particular point, these are the coordinate of this particular point here, x, y, z. Let's say it have some pressure which is Px by z, and obviously a function of time if it is getting changed with respect to time also. So unsteady state operation, then it has a velocity vector which direction it is going or the moving, and that also would change with respect to x, y, z at time point. So in case of Eulerian part, in case of the Eulerian, you are just focusing, let's say, at this boundary and this boundary. You are not focusing in between part here. Lagrangian part, you are focusing that what is happening from here to here for this individual particle. So if you are focusing on this particle, you are at Lagrangian part. If you are focusing at a cross section here, let's say at this end, then you are at the Eulerian part here. Fine. So this is the another example of Eulerian and the Lagrangian part here. Now let's say this is one of the example we already did here. So what you have here, you have a velocity field which is given that v equal to that 0.5 plus 0.8 x I cap plus 1.5 minus 0.y j cap. So the question is that a steady incompressible two-dimensional velocity. So two-dimensional means you will have two coordinates at that particular point, x and y, or x and z and y and z. Okay, so that will make you the two-dimensional. If your variables are there either x, if it is there only x throughout, then it's become one-dimensional. If it is have x and y, or let's say this velocity, you can differentiate it with respect to x, with respect to y, with respect to z. So if you are getting two derivatives, it is two-dimensional. If you are getting three derivatives, three-dimensional. If you are just getting one derivative, rest of things are the zero, it means one-dimensional. So that is the way to identify the dimensions of the flow. Or visually, you can also see if you have x, y, z present, three-dimensional, or any two coordinates are present, two-dimensional. If it is only one coordinate is present, then one-dimensional. Fine. Here you want x and y coordinates are in terms of meters and magnitude of velocity in meter per second. Now they want to say that a stagnant point is defined as a point where flow field, this velocity is zero. So you want to find the stagnant point coordinate where this velocity of this flow field is zero. It means your velocity should be zero. So how can you find out that? To make the velocity equal to zero, you must have the individual component of the velocity must be zero. So this is your x component of the velocity. Is that u? That should also be the zero. This is the another coordinate component of velocity. That should also be zero. Only then you will have the stagnant point. You have this direction velocity or your y direction velocity. Both the velocity component must be zero individually, and that will give you the coordinate. So if you will satisfy that here, so this is your u, 0.5 plus 0.8x, and you are forcing it to be equal to zero. You are calculating coordinate of x, then you are calculating v component of velocity 0, that is 1.5 minus 0.8 y equal to 0. So from here you are getting y equal to 1.85. So these are the coordinate of the flow field there at x equal to minus 6.5 and y equal to 1.875. Your velocity is coming 0. So, and now you want to, these are the coordinate of that particular point where velocity is 0. The B part here, that scales the velocity vectors at the location, then you have a domain there, minus 2 by 2. So you have taken a cross section there, minus 2 by 2 meters, and then you have y is 0 to 5, and you want to plot this, what will happen. So let's see here, if you just say plotting of your the streamline here. The streamline can be plotted for this or not? Hello? Any response?
Yes, sir.
So streamline, if you see here,
Yes.
so this is your velocity, this is your u, this is your v. So you can have means the streamline thing that what will you have there? Dy upon dx would be equal to v upon u, right?
Yes, sir.
Correct. Based on that,
Yes,
this
yes.
equation can be that can be derived also or plotted, or without that also you can do. How can you do that? Just change your x. Just put a particular value of x, right? Now you keep on changing the y. So you can get your v component of velocity. For x and y, you will get particular velocity component. Fine? Yes or no? For
Yes.
particular coordinate of x and y, you can keep on changing it and you can plot this and you will get that way also streamline. Or you have to streamline the equation, drive that fast. Based on that, this can be plotted here. Now this can be plotted. This is your mesh size they have the given to you, that minus 2 to 2. So this is here. Minus 2 is here and 2 is here. Then 0 to 5 here. So you are taking 0 here and 5 here. So in between of that, you are being asked to plot your velocity profile or the streamline here. Now you see at this point O, here, can you see this point O? This one? Here,
Yes, sir.
there's, because fluid is also moving this side, fluid is also moving this side. So in that case, here this particular point, your velocity is coming equal to 0 because your fluid is going this way. So at this point, your velocity is coming 0. So that is your coordinate is कितना है वो minus 0.65. That's what you got here. This is minus 0.625. This is the x coordinate of the velocity, where this velocity component is 0, u. And this is your y coordinate corresponding 1.875. So if you see the figure here, so here if you see here, so this is the component of means where is velocity equal to 0. Can you identify here the 0 part here? Where velocity is the 0 here?
Yes, sir.
कहीं दिखता है velocity 0? So this is the plot here. You will come to know here that is coming at this particular point here. So from this point, this is the half of the part. Same thing is this part only. So this would be your 0 point here, and that's where you are the plotting here. So the stagnant. So you have learned from here one point here, stagnant point. So stagnant point is the point where individual component of velocity must be equal to 0. There should not be any velocity magnitude in any of the direction there. Fine. Now we want to see the acceleration part. Late. So you have now, once you have velocity, and then obviously you will have acceleration because your velocity would come if there's changing with respect to time. So your fluid is getting accelerated here actually. So let's say at this particular time your velocity is different. After some time, you are going to say that your velocity magnitude is also here different. So that means your fluid is having acceleration. So it could be acceleration, it could be deceleration actually. So if magnitude of a particular parameter is getting decreased with respect to time, so deceleration, increase with respect to time, then the acceleration. So both the things are possible there. So now you are talking about all these laws, the fundamental laws are valid only for a mass. Yes or no? In case of the fluid, your mass, you are talking mass of individual particles because it have particle and fluid is combined of number of particles and you are taking as a fluid as a continuum, right? That's what we are talking in chapter 1, continuum fluid mechanics. So continuum fluid mechanics, the whatever mass you have within a particular confined control volume, your mass is not changing. Therefore, you can apply all these laws on that particular differential volume something. So that's what you applied all these fundamental laws on the materials. So the derivative now calculating on force or velocity and all these are called now the material the derivative in case of fluid mechanics because you are means the applying those laws on material only. Therefore the part the word came here material that mean the derivative. Sometimes also you can say substantial because material and substance both are same thing. Okay? So your force would be mass into acceleration. So acceleration is being calculated by dv upon dt. So this is the simple thing you have. Now particle have your velocity. It could be a function of x also, your function of y also, function of z also. So your velocity is function of x by z as a function of time. So if you want to calculate total derivative of v, so we have four components. One is x, one is y, one is z, one is t, right? So if you want to find total derivative of v with respect to t, so first you will partially differentiate v, so del v upon del t, multiplying by dt upon dt, so this would be the derivative of v with respect to t. Same thing now with respect to x, with respect to y, with respect to z, add all those derivatives, that is called the total derivative of this particular particle attributes. Okay? Is that fine till here? Total derivative. Find the derivative with the individual parameter, that's called partial, multiplied by change there. So that's where you can calculate your difference of a derivative. Or del v you can write in several ways. If you write here, so this will get cancelled. This is the derivative with respect to time. This is derivative with respect to time again del v upon the del t because this will get cancelled. Del v upon del t again with respect to time you are the multiplying two terms here dy upon del y here. This is again this will get cancelled, so you are just getting the derivative with respect to time. Now the first one is called this partial derivative here with respect to velocity, time here. So if you say acceleration here, now you are getting this. This t will get cancelled, so you will have practically this del p upon del t. How this velocity is getting fluctuated with respect to time. So you got one term there. This is called your local acceleration actually. The things with changing with respect to time. Now let's say this particular part here. So this you are getting from here del v upon the del x is okay, that's your present. Now dx upon dt, the movement of particle in x direction divided by dt, you are calculating now x direction velocity because you are just finding the movement in x direction divided by time. So that is your net velocity in direction x. So that's what you got here term u. So u is practically your dx upon dt. Net movement of particle in direction x divided by time. That is your u. Same thing for v. So this is dy upon dt. So movement of particle in y direction divided by time. This is the v component of the velocity. Same thing for here del v upon del z. So in z direction this one, the movement divided by time. This is again the w. So you got acceleration of the particle you can rewrite in this particular format here. Fine. So this total term here, if you say this particular term here, this one, last three equation, maybe I can. So this term, the underlying term here, this one, these three terms are called convective acceleration of the particles. Because this is just to their change in velocity in a particular particle. Okay, so that may change due to the motion of fluid particles only. Now this del V upon del T, this first term which is not underlined, this is called local the acceleration of particle. It would be just a function of time. Let's say you are putting energy at a, let's say at 5 minutes, every 5 minutes you are providing 100 joules. So your velocity would change only at every 5 minutes. After that, it won't change. So that would provide your local acceleration here. You are just providing at a particular time interval. Sometimes you are just providing that means every second you are providing 100 joules or 50 joules. Okay, so this first term is called local, that means acceleration of the particle, and this is called convective acceleration of the particles. Fine. So there's one more term here called, you can write here del operator. So del operator is given by this one, I cap del upon del x, j cap del upon del y, k cap del upon del y. This is called del operator actually. So if you have this velocity, you have this del operator is from here. If you multiply this, multiply by this v, you should get this derivation. So you just today you try to drive this the derivation whether you can do this vector v dot product of del multiplied by v. Are you getting this equation or not? Have you done the dot product or not of vectors? You did, no?
Yes, sir.
So your
Yes,
vector is here. Your v vector is what? V is what? You have u I cap plus v j cap plus w k cap, right? That is your v plus a time derivative part also. So this is for your v. So you are talking about convective, so you don't take time there. Now you have del operator. Del operator is given by this I cap del upon del x, j cap del upon del y, k cap del upon del y. So you have two vectors. Now you are doing dot products. So I dot I is how much?
one.
And
1.
I dot j,
0.
0. 0.
right? So that way you, if you will do it, you will get this equation back. Okay? So just you just try that. What will you get? So you will get that. So wherever you have I into I, you are getting u. So I would be there with u only. So you here you have this. So you will get I into I 1. You have u there. Then you have the multiplying this by this term v, so you will get this term here. That यहाँ पे v आ जाएगा सीधा. So del v upon del s. So you got u del v upon del s. You will get first term. Yes or no?
Yes, sir.
Then you will get the second term. Then you will get the third. So we will end this class here actually. So then you can write here acceleration. Previously you got total acceleration of the particle. Now because you have all 3D flow, so you want what should be the acceleration in direction x, what should be acceleration in direction y, what should be acceleration in direction z. So you can write total acceleration whichever you got in previous case. This is called total acceleration here. Now you want to write acceleration in x direction, y direction, z direction. So either you club all the component which goes into I cap, which goes into j cap, which goes into k cap. So you can segregate this line into 3 parameters. Yes or no? So if you will do that, so you are doing, this is x component of the acceleration. You are just taking everything of direction x component. So x component, what is your the velocity there? U. Yes or no?
Yes, sir.
So U. So everywhere V is being changed by U only. So say here also U, here also U, here also U, here also U. So you did everything for U. So this would give you the X acceleration. Same way for Y. So your V is being changed by small v there, capital V. So you have here V also, V and V. Same thing for Z direction, you have the W. So these three equations would give you your acceleration in individual coordinate X, Y and Z. Fine. So rest of the things we will do in the next class. Okay. So try to do that the derivation and try to find this also. Can you get this only also from that line? X component, Y component or Z component. Okay?
Okay, sir.
Okay then. We will close here.